All right, let's take a look at problem 18. Okay, use the epsilon delta definition of a limit to show that the limit as x approaches 7 of the function 9 minus x is equal to 2. What I want to do before I start solving the problem is, just as a reminder, I'm going to write down the epsilon delta definition of a limit. Okay, so the limit as x approaches a of f of x equals L means for every number epsilon greater than 0, there is a number delta greater than 0 such that if we have the case that x's are close to a, so 0 less than absolute x minus a less than delta, then the f of x's will be close to L. So f of x minus L less than epsilon. Okay. So when we go to do our proof, what we want to do is start with an epsilon, show that there is a delta by writing down what it is, and then assuming this first piece, we show the second piece. Okay, except that we have to work backwards so that we know what the delta is. Okay, so we're going to start with finding the delta. So we work backwards. We start with f of x minus L less than epsilon, and we work backwards towards what we're supposed to begin with, right? The x minus a less than delta. So we plug in the function f of x, 9 minus x, plug in the value for L, that's the 2. Okay, let's simplify. 9 minus 2 is 7. Okay, and what I want to work towards is x minus a less than delta, and the a is 7. So I want to get to x minus 7. I have 7 minus x, so I'm going to factor out a negative 1. So this will be negative 7 plus x, or I could write that as, put the x in front, so then it would be 7 minus x. Okay, and if you have two multiplied things in absolute value, you can write those as multiplied absolute values. And of course, the absolute value of negative 1 is just 1. Okay, so this first statement is equivalent to the second, which is equivalent to the third, and so on. These are all equivalent statements. Okay. All right, and now we have x minus 7 less than epsilon. And since we wanted to start with x minus a less than delta, the epsilon and delta should be the same. So we're going to pick delta just equal to epsilon. All right. The problem with this is that we did it backwards, so now we're going to rewrite it forwards. Okay. So now let's write the actual proof with the logic going the right way. Okay. So for any number epsilon greater than 0, we let delta equal epsilon. Then if 0 is less than x minus a is less than delta, that means that x minus 7 is less than epsilon. And then referencing our work over here, we just use these same steps backwards. So we don't have to write them down again. We already did the work. It's just upside down. Okay. So that tells us the f of x minus L is less than epsilon because we already did the steps to connect them. So that gives us the limit as x approaches 7. 9 minus x is equal to 2. Does that make sense? I suppose as much as I can. I know that these are the confusing problems, but okay, good. All right, is there another one you want to take a look at? So as soon as this is over, I'm going to go ahead and post up all of the answers worked out. So you'll have those available to reference. So my point here is to go through it in detail to kind of show you the steps. Did that one in class. Okay. Richard, did you have any questions that you wanted to go over? I mean, it's okay to not have questions. I mean, you know, it's perfectly fine to just show up, but $17. Yeah. So I'm not going to rewrite down that epsilon delta definition for this one because I just did that. But we start off the same way. First, we want to find delta. Okay. So we're going to start by working backwards. We start with f of x minus L less than epsilon, and we want to work our way back towards x minus a less than delta. Okay, and maybe just for reference, x minus a less than delta, the a is going to be a 3. So I'm looking for an absolute value of x minus 3. That's where I want to get to. Okay. So we go ahead and plug in the function, 6x minus 3. We plug in the L, 15. Okay. Simplify a little bit. Negative 3 minus 15 is minus 18. Since I want to get to an absolute value of x minus 3, and I have 6x minus 18, we're going to factor out a 6. And there's the x minus 3, so we say, oh, that's good. Divide both sides by 6. And now we have absolute value of x minus 3 less than something, and that something then is going to be our delta. Okay. So since these are all equivalent steps, right, or equivalent statements, okay, we're going to make use of the same steps going the other way. So let's go ahead and look at the logic going the correct direction. We have to start by saying for any number epsilon greater than 0, we let delta equal epsilon over 6. So we've shown that a delta exists because there it is. Then if 0 is less than x minus a less than delta, that means that x minus 3 will be less than epsilon over 6. And then using my steps backwards, that means that this is equivalent to this, is equivalent to this, equivalent to this, is equivalent to this. And that tells us that f of x minus L will be less than epsilon. And that gives us the limit. Okay. So it can get a little more involved when we have more complicated functions, but for a linear function, they're pretty straightforward, and it's going to look, you know, if you look at this one that we did, and at this one, it feels very similar, or hopefully should feel very similar, right? It's kind of the same steps. And there's no surprises or anything that pop up. If you put in a different function, right, put in like a reciprocal or something like that, a fraction, then we get surprises. But you won't have that on the test. All right, anything else? 14 and 15. All right. So the piecewise functions can be tricky, but this is also talking about continuity. So before I get going on this problem, we'll just have a little reminder of what it means to be continuous. So f of x is continuous at x equals a if we have three things. One, f of a exists. Two, the limit as x approaches a of f of x exists. And finally, these two match. Okay, so if I have all three of these things, then the function's continuous at a point, and if I'm missing any one of them, then the function's not continuous at that point. So the point in question for this problem is x equals 3. So what we want to do is check our three criteria. Okay, so we'll just run down the list. We start by saying, what is f of 3? My piecewise function says if x is equal to 3, we use this formula. The formula is just -1. Okay, so since I know what f of 3 is, clearly it exists. Right. So now I'm going to look at the limit as x approaches 3 of f of x. And that one is a little bit challenging because I don't have one single formula I can write for f of x. Right? There's different formulas depending on what x is. So I can see in my piecewise function, it splits. If x is less than 3, I get one formula. If x is greater than 3, I get a different formula. So what I'm going to do is I'm going to look at the left and right limits separately. I'm going to look at the limit as x approaches 3 from the left of f of x, and the limit as x approaches 3 from the right of f of x. And the reason I'm going to do that is because if I approach 3 from the left, then that means that the x values are all smaller than 3. And if the x values are smaller than 3, then I have a formula, 5 minus 2x. So this is going to be the limit as x approaches 3 from the left, 5 minus 2x. And because 3 is in the domain of this polynomial, I can just use direct substitution to find the limit. And I get -1. So we do something similar over here with the right-handed limit. Because I'm approaching from the right, the x values are all going to be greater than 3. And my formula says for f of x, use x minus 1 squared if the x's are greater than 3. So we're going to look at the limit as x approaches 3 of x minus 1 squared. And again, I can just use direct substitution. And I get 3 minus 1 squared. 3 minus 1 is 2. Squared gives me 4. And here's where we run into a problem. -1 and 4 don't match. The left and right limits don't match. That means that the limit doesn't exist. And since that limit doesn't exist, the function is not continuous at x equals 3. Okay. Any questions on this one? Okay, so let's go ahead and take a look at 15. So there's a couple of parts to 15. First, setting up and solving the problem using this idea of continuity is this should be pretty straightforward, right? So we'll go through that, and that should make some sense. And then actually solving for a and b, it turns out, is a lot of messy algebra. Okay, so we're going to focus more on the first part of the problem, and I will do the whole problem, but that second half where we're just solving equations to get the a and the b is going to take a little bit of effort and a bit of time. So I don't want you to get too lost in the problem. We want to focus on this first part where we set things up. That's going to be the important piece to sort of carry with you into the exam. All right, so find the values of a and b that will make this function continuous, right? So the idea is that for different numbers a and b, my function will look differently, and I want to pick the ones that will make everything match up very nicely. Okay, so like if I pick different numbers for a here, I'm going to get this, this piece might be taller or shorter, right? Here I'm changing the slope and intercept of the line that's for this piece, right? And here I'm changing the slope of this line. So that's just going to affect where, where the graph is, and we want to make sure that everything lines up. So if I just look at one of these at a time, these are going to be continuous functions, right? The second and third one are just lines. They're always continuous. And this first one, the square root function, is continuous on its domain anyway. Okay, so it'll be fine. The only thing that we need to worry about is where they connect up. Do they actually connect to each other? So we're going to focus on -1 and at 3. So if I want to make f continuous, then f needs to be continuous at -1. And just like we saw above, that means that the limit exists, so the left and right limits have to match. So what we do is we say, all right, the limit as x approaches -1 from the left of f of x must equal the limit as x approaches -1 from the right of f of x. Okay, so let's work out what those limits are and then set them equal to each other. Okay, so for the limit as x approaches -1 from the left, my x values are all less than -1, so my function is going to use the formula square root ax squared. And then I'm going to evaluate this limit using direct substitution. -1 squared is 1, so this is just the square root of a. Okay. If I look at the limit as x approaches -1 from the right, the x values are bigger than 1. Both of these formulas, right, are looking at x values that are bigger than 1, right? Because if you're bigger than 3, you're certainly bigger than, you're bigger than -1. The thing, though, about a limit is we're thinking about what happens when we get infinitely close. Okay, so we don't want to use this formula where we're bigger than 3 because 3 isn't very close to -1. We want to think about as you get closer and closer to -1. Okay, and so that's going to be, these x values here. So we're going to use this formula here. Okay, so we're going to take the limit as x approaches -1 from the right of ax plus b. And it's x that's approaching -1, so I'm going to evaluate this limit using direct substitution by plugging in for x. So I have a times -1 plus b, or just -a plus b. Okay. So if I want this function to have any hope of being continuous, these left and right limits have to match so that that limit exists at x equals, the limit as x approaches -1 exists, right? So, so we have square root of a has to be equal to -a plus b. That on its own isn't going to be enough to do anything, but it gives us an equation. But I have these two unknowns, a and b, right, that we've always had that we want to find. But now I have an equation with a and b. That's helpful. So now what we're going to do is we're going to look at another point. At 3, right? That's the other place where things change, right? Our formulas change. So we're going to go through the exact same thing. We want the left and right limits to match. So the limit as x approaches 3 from the left of f of x must equal the limit as x approaches 3 from the right of f of x. Okay, so let's look at what those are. As x approaches 3 from the left, we're looking at x values near 3 but smaller than 3. Okay, so that's these x values. So I want the formula ax plus b. And when I do direct substitution, I'm going to get a times 3 plus b, or 3a plus b. Okay. If I look at the limit as x approaches 3 from the right, the x values are bigger than 3. So I'm going to use the formula bx plus 2. So I evaluate this by plugging in for x. We get b times 3 plus 2, or 3b plus 2. So we have 3a plus b is equal to 3b plus 2. Okay, so that's the part of this problem that I think you really want to focus on. This is the important part of the problem right here. Now, we're going to have a significantly longer part of this problem where I actually figure out what the a and b are by solving these equations. Okay, so it's two equations with two unknowns, and we should know how to do that, but I'll go through it anyway, but in this case, it gets a little bit dicey. Okay, so what we want to do is solve for one variable and plug in for the other. What I'm going to go ahead and start with, I don't really like the square root over here, so I might want to square both sides to get rid of it. Okay, so if I take square root of a squared, that's going to be equal to negative a plus b squared. On the left, square root of a squared will just give me a. And on the right, I have to FOIL things out. So I have negative a times negative a, that's a squared. Negative a times b is minus ab. And then I'm going to have that again, right, the inners and the outers, and then plus b squared. Okay. Okay, so simplifying things a little bit, we're really just gathering like terms. Negative ab minus ab is minus 2ab. All right. What we really want to do, though, is pick one of these equations and solve for either a or b and plug into the other one. This equation's too messy, so I'm going to use our second equation over here, and then I'm going to solve. I can solve for either a or b. Doesn't really matter. So 3a, if I just subtract b on both sides, I'll get 3a equals 2b plus 2. And I don't know, maybe we'll just solve for b. So 3a minus 2 equals 2b. And then I divide both sides by 2. So 3 halves a minus 1 equals b. Okay, so what I'm going to do is I'm going to take that value for b, and I'm going to plug it in for b into the other equation. That will get rid of the b variable. So I plug in 3 halves a minus 1 for that first b, 3 halves a minus 1 for b in the second one. Okay, let's clean this up a little bit. We're going to distribute negative 2a to both terms. So negative 2a times 3 halves a, the 2's cancel, and I get minus 3a squared. And then I take negative 2a times negative 1, and I get plus 2a. Okay. For my second piece, again, we have to FOIL this out, right? So if I take 3 halves a minus 1 times 3 halves a minus 1, right? When I take the first terms multiplied by each other, 3 halves a times 3 halves a will give me 9/4 a squared. Okay, and then we do the outers. 3 halves a times negative 1 will give me a minus 3 halves a. Negative 1 times 3 halves a will give me the same thing, minus 3 halves a. So I have two of these terms. And then negative 1 times negative 1 is plus 1. These 2's cancel. Let's go ahead and gather some like terms I'm going to subtract a from both sides to get the a's together. So 0 equals a squared minus 3a squared will give me a minus 2a squared. 2a minus a gives me a plus a. And then I have minus 9/4 a squared. And over here, this is a minus 3a. Okay. A minus 3a is a negative 2a. And I don't really want to work with fractions if I can avoid it. So what I'm going to do is I'm just going to multiply everything by 4. 0 times 4 is still 0. So I have minus 8a squared minus 8a. The 4's here cancel. And then this guy will have 4 on it. So now I have 9a squared minus 8a squared will give me just a squared minus 8a plus 4. Okay, well, that's a nice quadratic. Okay, we can solve that easily enough. I'd like to factor it, but I can't see how to factor it, and I think that's because it doesn't factor. So we're just going to jump straight to the quadratic formula. Now, what can be confusing about the quadratic formula is that we typically have either x's or, it's usually like an x squared type of thing, or maybe y's or something. And then there's like a, b's, and c's in our quadratic formula. Well, now a's and b's are already used up. So we have to be a little bit careful. If you like, you can change the variable. Instead of talking about a squared, you can just write it as x squared to do the quadratic formula, if that would be less confusing. Okay, and we'll just come back to a at the end. Okay, so if you want to, you could say, okay, I want to solve x squared minus 8x plus 4 equals 0 using the quadratic formula. Okay, and that way the a's and b's and c's in the quadratic formula don't get confused with a over here. Okay, but you don't have to change a variable over. If I do that though, or whether I do that or not, right, the number that I want here, this negative b, well, the b in this quadratic formula is the coefficient on the x. It's a negative 8. When I take the opposite of that, I get 8. Okay, negative 8 squared is 64. The a is the coefficient on the x squared, which is 1. And the c is a positive 4. Okay, so I have 8 plus or minus the square root of 64 minus 16 all over 2. So I have 8 plus or minus the square root of, I think that's 48 over 2. Okay. So I'll go back to calling it a's again. So a could either be 8 plus the square root of 48 all over 2, or a could be 8 minus the square root of 48 all over 2. And I'm going to simplify these down a little bit. Now, with this square root, I think that you'll probably remember from like an algebra class, you pull out as many factors of 48 as you can, and then, you end up with it simplified. If you don't want to do that, that's fine, but it'd be nice to at least cancel the 2. So I would look at this and say, is there a factor of 4 that I can factor out? Then when I take the square root, I get a 2 and cancel with this 2. Okay. I'm gonna go ahead and factor this a little bit further. Now, I'll factor it all the way down, but if you only wanted to factor a 4 out, that would probably be okay. Square root of 12 isn't really a bad thing. Right? Okay, but I'm gonna go ahead and write this 48 as its factors, right? So I know that there's a 4 in there I could factor out because this is 4 times 12. And 12 I can write as 4 times 3. So I can break square roots up over multiplication. So this is like 8 plus the square root of 4 times the square root of 4 times 3. And the square root of 4 is just 2. Okay. So now I can take a factor of 2 out of the numerator and cancel with the denominator, and I'll just get 4 plus, oops, I lost my root on the 3. 4 plus 2 root 3. Okay. And this one is the exact same thing except with a negative. So this would be 4 minus 2 root 3. Okay, so now we have a number for a. And then going back, b was 3 halves a minus 1. Okay, so that's 3 halves times 4 plus 2 root 3 minus 1. 3 halves times 4 is going to be 6. 3 halves times 2 root 3 is going to be 3 root 3. So I'm going to get 5 plus 3 root 3. Okay. For the other one, we have 3 halves, value of a minus 1. 3 halves times 4, right? If I do the division first, it's easier. Make it 6. 3 halves times 2 root 3, the 2's cancel, so we get minus 3 root 3. And the minus 1's hanging out, so again, I'm going to get 5, and then this time it's minus 3 root 3. Okay. So I have these two possibilities, right? I can have this for my a and this for my b. Or I could have this for my a and this for my b. Okay, well, this problem gets one step more complicated because I'm not really just done here. I need to actually check and see if these work. And I'll explain why we end up with a bad solution here after we show it. But what I want to do is just see, do these actually solve my original equations? Okay, and in particular, can I even plug them into that square root? Okay, or maybe I should just use the more simplified version of the equation. I don't know. So let's just check this. Let's check. Let's check my original equation. Okay, both of them, and I'm just going to plug them into my calculator. I need to make my calculator visible here. Okay, so hopefully now you can see my calculator. And what I'm going to do is I'm going to take this first value for a and b, 4 plus 2 times the square root of 3, and then 5 plus 3 times the square root of 3. Okay. What we're going to do is we're just going to go back to our two equations that we wanted to solve and make sure that it does that. So if I look at my first equation, that's the square root of a. So I go up and grab my a value and put it in the square root, and I get a number. And then I'm going to have negative a plus a value I got for b. Okay, and I can see these two sides are equal. Now, almost, the very last digit is off a little bit, but I think that's just calculator rounding error. So I'm not going to worry about that, right? But all the other digits line up. So I say, okay, the first equation, they match up. Let's check the second equation. So I have 3 times a, go here and grab a, plus b. I get some number. Now I'm going to take 3 times b plus 2, and again they match up, right? Except the last digit by a little bit, that's just calculator rounding error. Okay, so this first a and b that we got really does solve the set of equations that I wanted, which means that the function is going to be continuous. Now let's look at the second set, the a and the b. So I have 4 minus 2 times the square root of 3 And I have 5 minus 3 times the square root of 3. Okay, so that's my A and my B. Let's go back and look at our equation. So here's my square root equation, right? Square root of A gives me that. And I'm going to take negative A plus B. Negative A plus B. And they don't match. They're the same number, but the second one is negative, right? So it doesn't work. What happens was, when we were solving this equation to get rid of the square root, we squared both sides. And if I look at these two numbers and I squared them both, then they would match. And that's why we ended up with this fake solution, because it does work for what we were solving, but not our original equation. When we squared both sides, we created a fake solution. Okay, so this one doesn't work. Okay. This one does. Okay, now to answer the question that you probably didn't ask, but maybe you're worried about, are you going to get a question like this on the exam? And what I want to emphasize is that this first part up here in blue, that's something that you can definitely see on the exam, right? Where, you know, maybe you find some values that'll make a function continuous. You have to know about continuity, and you might set up some equations. These particular sets of equations, that was a lot of work to solve for A and B. But this isn't like calculus work. This is algebra work. And we do a lot of algebra in calculus, but this is not a good exam question. You won't see a question that requires you to do all of this. And then even after all that work, you have to check because one of the solutions doesn't work. Yeah, you're not going to get something like that on the exam. So, I mean, I have it on here on the practice, but it's really this first part of the practice that I really want to emphasize here. And if you did have to solve the equations, the one on the exam would be something that would be simple. It would be quick and easy. You wouldn't have to, you know, do a bunch of steps and quadratic equations and stuff like that to solve it. It would be something quick. Okay. All right. Does that make sense? Okay, good. Any other questions? I think we only have time for maybe one more, if it's a long one like this. Okay, if you're all set, I'll go ahead and post up the answers to all of them so that you can check everything that you did as you went. And we should be good to go.